Hey everyone, today we're going to be looking at binary tree level order traversal. Now, this is a breadth first search problem. It says, given the root of a binary tree, return the level order traversal of its nodes values, i.e. from left to right, level by level. Well, okay, what if we had some sort of system where we could look at each level individually, move we go from 3, and then we look at all of its nodes, and then we go to 9 and we look at all of its nodes. There's nothing in this case. We go to 20 and we look at all of its nodes. Well, fortunately, there's an algorithm for that. It's called breadth first search. Hey, I just noticed I didn't put in a joke here. Well, maybe we'll get to a joke later. But for now, try to concentrate. Okay, what we need is let's just kind of intuitively do this as we go along. Okay, so first we'll do our little sanity check. If root equals null, if there's nothing in the root, return the 2 accolades, and that's standard language. In order to do the breadth first search, you need a queue. So we're just going to be queuing each level up, and whatever's in the queue is going to be whatever we have to look at the particular level at any given time. If we stacked up 3 in the queue, we're done for level 0. Then we stacked up all of 3's associated nodes, and the next time we look at the queue, we iterate through everything that's in the queue. It'll be the 9 and 20. At that point, once we iterated through that, we're going to have stacked up all of its numbers, and then the next level will be all of those numbers in order. So that's how we're going to proceed. So let's come up with first our return value, which is they ask for a vector of integers. And we know that after all this, we're going to have to return my return. You know, if you have nothing else to do during your interviews, you might as well get the setup right in any particular situation. So what we need for the breadth first search is, let's see, a queue, which is a first in, first out. So there you go. Type of structure, which we're going to call my queue. And actually, this queue is going to hold not integers, but nodes. Okay, so it's going to be a queue of nodes. Next, we're going to immediately put in the first node. And we could do this as follows. We just push in the root. Now, here's the crux of it. While the queue's not empty, so we keep on doing stuff until the queue stops being empty. Let's see how we do this. So since we're going to be adding stuff continuously to the queue, and we're going to iterate through the queue, we want to get the size of the queue immediately. So why is that? Because the size is likely to change. If you're iterating up until the end of the queue and you're at 3 and you already stacked up 9, suddenly it's going to get confused. So let's just immediately mark that down. Queue size equals my queue dot size. Now let's see. Oh yeah, and we need something which we're going to push into my return at every level, and that's a level, which is a vector of integers. That's what they asked for. Current level. Okay, so we have everything we need for that. And now we could iterate through the queue according to the size of the current level of the queue, which we marked on queue size over here. So I smaller than queue size, I++. Now the first thing we're going to want to do is get the current node that we're looking for. So tree node current node equals myQ.front. Okay, for a stack, you're looking at the top. On a queue, you're looking at the front. So you just want to immediately push back the current node.val. So that's going on our current level. We just stacked up 3 over here. And now we want to add to the queue those related nodes. So we just want to check. So if we just want to check if 3, for example, has related nodes. So if current node dot left not equal null, then my queue dot push current node dot left. Okay. Now we could do the same thing with the right. Just do a little copy paste type of thing here. And when we're done with this particular node in the queue, well, we could just pop it. Likewise, for every time we're done with a particular level, we got the current. Every time we got this particular level, we filled up that level vector, and therefore, before moving on to the next level, we have to push back the current level into my return. And I think that's it. Let's test that. And we have a winner. That's it, everyone. Thanks for watching.